Good morning. Today we're going over atomic and subatomic theory. So atomic theory is the theory that all matter can be broken down into individual fundamental pieces. It comes from the Greek word atomos. And those are pieces that cannot be divided further. And what we find is that we know matter can be divided into two types of pure substances. There are elements and compounds. And we find that all the compounds can be further divided chemically into elements. So everything is made of elements, and the smallest particle of each element is the atom. So the atomic theory that we will be looking at was outlined by John Dalton, the father of atomic theory, and it has four central tenets that you'll need to know. So atomic theory, let's see, says, number one, all matter is composed of atoms. Those are the smallest pieces of any type of matter. Atoms. And number two, all atoms of a given element differ in substantial ways from atoms of all other elements. We're saying essentially what it is that makes this element silver and this element gold has to do with some fundamental difference between the smallest particles of those elements. So the atoms of silver would have to be different from the atoms of gold. So number three here, we find that compounds are combinations of atoms. And one thing that's very important to note is that each molecule of the same compound has to be identical. That is to say, they have to have the same number and types of atoms. And this is the same thing as what we talked about before, where we said matter, pure substances have a constant composition. So this is another way of saying compounds have a constant composition in terms of the atoms that they're made out of. So number four, atoms are not created or destroyed by chemical reactions. Now, chemical reactions are reactions which change the identity of a substance. And so in that case, we would be looking at, for instance, taking a compound and breaking it down into its component parts. So we have a different identity of pure substances that we're looking at. For instance, water versus oxygen versus hydrogen. So that's a chemical reaction. That's different than like a nuclear reaction, where it is possible for matter to be created or destroyed. But for the most part, the vast majority of this class will be looking at chemical reactions only. So if you look at your periodic table in front of your book, or if you look at the periodic table that we use for the class, let me pull this up here, we'll see that there are a bunch of atoms, bunch of elements. You may recognize some of them more than others of them. This periodic table doesn't include these last six elements here. But the truth is that everything up above about 93, as you see those numbers in brackets, indicate that these are not stable elements. They only exist for a fraction of a second usually, and then they decompose. And so even though we can say, yes, there are more elements that we could put on this periodic table, they're not anything that you're going to be working with in this class. A couple of other things to note. This is like one I'll give you on the exam. There will be symbols and names, so you don't have to memorize the names or the symbols of any of these. You don't have to memorize the periodic table. And in this one, actually, it's a British English. So cesium, Master in Chemistry probably wants to spell that just C-E-S-I-U-M. Cesium is the proper English, American English spelling of that. Again, British English says this is aluminium, but American English would just be aluminum. So just be kind of aware of that. So this is something I would provide you on an exam. So these elemental symbols, they do a pretty good job of representing elements in their pure state. So if I have carbon, then I might just say I have the symbol C. It represents carbon. And if I have oxygen, then I would use the element symbol oxygen. But if I'm looking at a compound, then we're looking at, again, these specific ratios, these combinations of atoms, and each molecule of the same compound has the same number of types of atoms. And you know you can't have like half of an atom, because that's the whole point. They can't be divided further. And so compounds are going to have a set ratio of whole numbers of atoms. So the way that we represent that is to use this symbol with a little subscript to indicate how many of each of those there are. So again, the element carbon, we say that's just C, but the compound carbon dioxide, and I'll teach you how to name these later in this semester, that's going to have 1 carbon and 2 oxygens. So that little 2, that subscript indicates that there are 2 of the atom that's represented by that symbol in the molecule. Or for instance, if I gave you the formula H2O, then you would understand that this is representing a molecule which contains 2 hydrogen atoms for every 1 oxygen atom. And I could even give you really complicated things like BaNO3, parentheses in structures like this do exactly the same thing that parentheses in math do. That is to say that this 2 multiplies through the entire set of parentheses. So this is indicating a compound which contains 1 barium atom, 2 nitrogen atoms, 6 oxygen atoms. Okay. Now you might say, why don't you just write it like BaN2O6? That makes a lot more sense. Well, it kind of would make a little bit more sense in that you don't have to do this extra math, but this is trying to indicate something about the structure of the compound that's given. And it actually makes it a little bit clearer for us to understand what type of compound that is. So that's why they do represent it that way. All right, next we need to talk about subatomic theory, because it's true that all matter is formed out of atoms, and atoms are the smallest unit of any matter that we've got here. But of course, us being scientists, that's just not enough for us, right? We have to ask the next question, which is then, well, what is matter made out of? What are atoms made out of? Are they really not divisible? Okay, so what we determine is that atoms are made out of smaller particles. Now, we don't say that these smaller particles are the smallest unit of matter, only because matter as we know it, those smallest particles are atoms. So the smallest piece of gold that still counts as gold is an atom of gold, for instance. And you can pick that atom of gold apart into smaller pieces and it ceases to be gold entirely. And you can't build a desk or a chair or a ring or any other item or thing out of any of these smaller pieces. But they're interesting and useful to know to understand how atoms work. So we're going to talk about them. They're called subatomic particles. And at the moment, we're just going to look at 3 subatomic particles. We have protons, neutrons, and electrons. And each of these pieces has their own properties, and they also have an interesting location distribution within the atom. So for instance, protons are positively charged particles. They have a charge of +1 relative to the other particles. So it's not actually useful for me to say they have a positive charge. You might say positive how much? Because we can actually measure charge. And we're just going to say, relatively speaking, protons have a positive charge, +1. Electrons have a -1. That is, they're equal and opposite to the protons. And neutrons have a charge of 0 relative to protons and electrons. So neutrons are neutral. So those are the relative charges of each of those. In terms of mass, protons have a relative mass of 1. Neutrons weigh about the same, that are also 1. And electrons are very small, so they weigh about 1/2000th as much as a proton or a neutron. And 1/2000th is so small that for all intensive purposes, we just say, look, it's basically 0. It has no mass. Now that doesn't mean it really is 0 mass. It just means it has 0 relative mass when compared to protons and neutrons. Finally, we find that protons and neutrons are located in the nucleus, that is in the middle of the atom. There's a tiny, hard, dense mass in the middle that's called the nucleus. And then the electrons are found in a kind of a soft, squishy cloud or area of electron density that surrounds the outside of the nucleus and the outside of the atom. So in the, what we'll call the electron cloud, maybe, depending on how you're characterizing that. So just to give you an idea, here you've got an atom, the little nucleus, and out here is your big electron cloud. And it really is this tiny, tiny nucleus. If an atom is the size of a football field, the nucleus would be the size of a grape on the football field in the middle. So that's how tiny the nucleus is compared. And then the rest of this is mostly empty space. It's not filled with electrons. They're just running around in that empty space. Okay, so let's take this back to identities of individual elements and say, what does it mean that you've got protons, neutrons, and electrons? How does a gold atom compare to a silver atom in terms of these subatomic particles? And we have 3 different things here. What we find is the first one, protons, this will define the element. Also what we call the atomic number. So on your periodic table, the number that's given right at the top here, that 1 for hydrogen, 2 for helium, 3 for lithium, 4 for beryllium, and so on and so forth, that is the atomic number, and that's the number of protons found in the nucleus of an atom of that element. So an atom of phosphorus has 15 protons by definition in its nucleus. The number of neutrons does not define the element because, of course, that's the job of the number of protons. Instead, what the number of neutrons does is it will contribute to the mass of the atom, because it doesn't contribute to the charge, but it does have a mass here. So it contributes to the mass of the atom. It does more than that. It actually stabilizes the protons, because here you've got a whole bunch of positive charges right next to one another, crammed together in the nucleus, and they're going to try to repel one another, and the neutrons help buffer that. And we find when we look at nuclear chemistry that you've got to have a good ratio of protons to neutrons for any atom to be particularly stable. So they do that, but they'll contribute to the mass of an atom, and we'll come back to that again in just a little bit. Finally, the electrons are going to contribute to the charge of an atom. And the reason for this is the protons are fixed. They define the element and they're in the nucleus, which is really hard to get to. It's right at the very middle. But as atoms react with one another, and as one atom comes into contact with another atom, it's these electrons on the surface that are interacting. And it might be that one electron gets transferred from one atom to another, and that gives the atom a charge. That is, it has a positive charge or a negative charge, maybe a positive 2 charge, maybe negative 2 charge, so on and so forth, depending on how many electrons were gained or were lost. And so if I gain extra electrons, then I'll have a negative charge. And if I lose electrons, then my atom overall will have a positive charge because it will have more protons than electrons. So you can hopefully see how that works. But if you would like, there's a little formula I can give you that basically says the number of protons minus the number of electrons. That's going to give you the charge. See, because then if you have more electrons than protons, your charge will be negative and so forth. Whereas for here, the number of protons plus the number of neutrons, that gives you the total mass of an individual atom. Okay, so if I have two things that have a different charge, we call them ions. So for instance, I could have a magnesium +2 ion, magnesium +1 ion, or I could just have the magnesium atom that would be neutral. If I have different masses, I'm going to call these isotopes. So for instance, I could have a chlorine 35 isotope. That's a chlorine with a total mass of 35. And I could have a chlorine 37 isotope, and it would have a total mass of 37. And you can see by your periodic table, for instance, that chlorine has a atomic number of 17. That means it has 17 protons. So if I have 17 protons but a total mass of 37, that means I must have 20 neutrons. Whereas in this case, if I have 17 protons, because by definition, if I'm chlorine, I've got 17, then this isotope must only have 18 neutrons, right? So these would be two isotopes, but they'd both be chlorine, and chemically they would react in the same way. So interestingly enough, if we look on the periodic table, you're going to see some masses here that are fractions. 35.45, for instance. Oxygen's nice, that's an even 16, but still you can't actually have half of a mass because you can't have half of an atom, and each of our subatomic particles either weighs 0 or 1. The reason that you've got some atoms or some particles that have apparent half masses on the periodic table is because the masses on the periodic table are weighted averages based on abundance. So what does that even mean? That means that if I have in front of me a sample of chlorine, then it has a whole bunch of chlorine atoms, like billions and billions and billions and billions of chlorine atoms. So I'm not really interested in what the mass of each individual chlorine atom is, because I can never even measure one chlorine atom. But I'd like to know on average what the mass of my chlorine atoms is so that I can predict, for instance, how much of something else that it might react with. So what we do is we look at all the chlorine atoms, we try to take the mass of as many as possible, and we say, hey, look, this is really interesting. I've got a lot of chlorine atoms that have a mass of 37, and I've got a lot of chlorine atoms that have a mass of 35. Both of these appear to be quite stable, actually, and oddly enough, I don't see any chlorine atoms with a mass of 36. That must just not be a stable isotope. So we've got chlorine with a mass of 37 and chlorine with a mass of 35. And so I could say that the average mass is 36, but that wouldn't be quite true because, as it turns out, about 78% of the chlorine atoms I discover have a mass of 35. And then only the remaining 23% have a mass of 37. So both of those are abundant, both of those are stable, but it's not half and half. So it would not be appropriate to say that the average mass is 36, because on average, I'm going to get more chlorine atoms with a mass of 35 than 37. So the best way to solve this problem is to take the mass of each isotope and multiply it by the abundance that's given. So I'm going to say, look, I've got the mass of 37, and at 23%, I'm going to multiply that by 0.23. And then I'm going to add that to the mass of the next isotope multiplied by its relative abundance. So I'm going to add that to 35 multiplied by 0.78, 78%. And I can do this with as many stable isotopes as exist for a substance, for instance. But if I plug this into the formula and just say every individual mass multiplied by its relative abundance, added together, then I'm going to get what is called the average mass. But it's not an exact average, it's a weighted average. And so if I was reporting these values, I would say it appears that given these numbers, the average mass of a chlorine atom in a naturally occurring sample is approximately 35.81 atomic mass units. And so that's how they get, for instance, the masses that are on the periodic table here. So chlorine is reporting 35.45, bromine is reporting 79.9. Incidentally, that looks like it's about close to 80. So you would presume that bromine with a mass of 80 would be the most abundant isotope, and it's not. It doesn't exist, just like chlorine 36 doesn't exist. Bromine exists in almost a 1-to-1 ratio of bromine 79 and bromine 81. So it's kind of an interesting thing. You wouldn't necessarily know based on the number here what the most common isotope looks like. So in your homework, you've got a couple questions that are looking at masses of individual atoms. And in those cases, do be careful. They are looking at the masses of a specific isotope, that is, that has a specific number of protons and neutrons. And they're not looking for you to just report the mass that is on the periodic table. So if they're talking about isotopes, make sure that you are paying attention to that. All right, that is it for this lecture. Tune back in for our next lecture on the periodic table, how it's set up, and electronic configurations. It should be a good time. Have a great day.